Hi, we're Group 5, and this is our final design presentation on the GeoBud. This is a brief overview of what we'll be going over today. Now, what is the GeoBud? The GeoBud is an Arduino-based GPS tracker that is able to detect the user's location coordinates in latitude and longitude and send them via text message to any mobile device. To receive the coordinates, the user just has to push the button on the GPS tracker and they'll receive the location as shown in this video.
So yeah, after we press this button, then it sends us the latitude and longitude coordinates. Yeah, and we just got it.
Our problem statement is to prototype and test a tracker that is able to detect the user's location and send the coordinates via text message. The goal of our group was to create a GPS tracker that is simple to use for people of all ages, specifically children. The user just has to push a button for their loved ones to receive the coordinates and know that the individual is safe. Individuals can use the tracker as an extra safety measure, for example, in cases when their phone battery is dead and they have no way charging it to let someone know that they are safe. We have created a prototype that is easy to use on a daily basis and doesn't require a lot of maintenance while allowing the user to feel safer.
Hello, my name is Nabiha and I'll be doing the requirements constraints for the minimum for GeoBud. For the minimum viable product for the requirements is the user interface must be easy to use. The GPS must be able to send text messages to the phone that it's connected to, and the location of the GPS must be accurate. The location of the GPS must be provided in longitude and latitude coordinates with an error rate of less than 1%. All three of these minimum viable product for the requirements has been met for our GeoBud, hence successfully solving the problem posed in the problem statement. For our minimum viable product for the constraint is the device must be able to run for 12 hours with the battery that it has. The GPS tracker must not exceed 200 grams. 80% of the weight should be the internal parts and the 20% should be just the casing in itself. The material cost of the prototype must be less than $150. We did have to order extra chip because our chip wasn't working previously, so we had to order a new one. Even ordering after the new one, in total, everything is less than $150, and it will be divided among 4 members of the team. For MVPs and future work to improve our GeoBud, we have incorporating an emergency option. This option can be used to inform the police that the user is in danger and send their coordinates. A hand power generator that charges the battery. This would require more skills as we would have to utilize DC motors. Another thing we have is instead of having a separate components for the GPS being interfaced with the Arduino, we could instead design a PCB board that includes all of our required circuitry on a much smaller board. And this would reduce the size of our casing and the internal hardware. Customizing casing options for a user to choose from is another thing that we want to improve on. This would be beneficial if this product were to be sold in the market. And last but not least, another thing we can improve on is we could make the GeoBud turn only when it is required, hence reducing the power usage. In all of these future work to improve our GeoBud, we would need additional features and some extra components that we might have to order and a bit more time to understand how to implement these extra features in the GeoBud.
So the system was built using an Arduino, a 7800L chip, a Neo 7M chip, and it also included a 3.7 volt battery, which was 5,000 milliamp hour capacity. It's a lithium ion rechargeable battery. So the basic premise of this device that we have was that it takes an input from a button that we have placed on the exterior of the encasing, and when it receives that input on the Arduino, then it'll send the location to the phone, and the phone number would be preset into the system, into the Arduino. And these longitude and latitude values would be taken from the Neo 7M and converted into a readable value, which can then be transmitted back to the user through a text message. One thing we had to consider was the SIM 800L chip and its power demands. So what it needs is at least 2 amps current, and this battery we have is 5,000 milliamp hour, which greatly exceeds that the maximum current that the SIM 800L needs. And the battery would also be providing power to the Arduino.
Hi, my name is Ali. This is the prototype system block diagram for the hardware. As you can see, we got the Arduino Uno, we got the SIM 800L, the Neo 7M, and our lithium ion battery. From the Arduino, we can see that we can either plug it into the laptop or we can plug it into a DC battery, a 9-volt battery. And when we made our final product, we wanted to be independent from the laptop, so that's what we do. We connect a 9-volt battery to the Arduino, and that drives its input-output pin logic, and the battery does the heavy lifting by powering the chips. And we'll see in the next slide what this looks like in reality.
The SIM 800L, the main reason we selected this is because it was a low cost and it's 2G compatibility, which reduces complexity. The low cost is because it's 2G compatible, and currently we have 2G compatible satellites, cell towers. So this is why we chose the SIM 800L. The Neo 7M, we also chose this because of its low cost, and it also has fairly good accuracy in this location, and it's also very simple to use and program on the Arduino. The Arduino, due to its low cost and it's also readily available, the biggest feature of the Arduino is that it's very easy to integrate components because it has very easy labeling for I/O pins and as well as power pins, and it also has a very good GUI for programming in order to make it simpler for us to program the device. The encasing was made of PLA, and this was taken into the biggest consideration that was taken in was that PLA is a very low cost material and it's also very readily available and it's quite durable for our use case.
So on our left, we got our simplified code diagram. And this code diagram, it first starts, it waits for a bit, it sees if the Neo 7M has connected to a GPS satellite. If it has, then it moves on to the next step. If it hasn't, then this step just keeps looping until it has finally got a connection. So from that connection, we can get the latitude and longitude coordinates, send them over to the SIM 800L via the Arduino, and the SIM 800L can send that as a text message to us. Now, this code diagram, again, is very simplified, and our actual code can be found on GitHub under this link. And keep in mind that the start on the code diagram will only begin when the button has been pressed. And we also used multiple other testing codes on each chip before making the final design code. And this was very helpful because of this, we noticed that one of our chips was faulty. And moving on to the problems and challenges. The first Neo 7M chip that we had was faulty, it broke. So we noticed that the chip was faulty when we ran the testing codes and it wouldn't connect to a satellite. And then we tested the resistance between the RX and TX pins on the broken chip and it was 0 ohms. Now, for comparison, the working Neo 7M chip that we ordered a second time had a resistance of 9 mega ohms approximately. And the SIM 800L was not reading 3G SIMs. That was another issue that we were having, like specifically TELUS 3G SIMs. Now, we know that the SIM 800L was made to be used on 2G networks, but 3G SIMs are backward compatible with 2G technology, provided that the carrier has not taken down its 2G networks. Now, that second part is very important because the reason that TELUS 3G SIMs weren't working was because TELUS took down its 2G networks in 2018, whereas Freedom Mobile still has them up, and with them, we were able to work the SIM 800L.
As you can see on the screen here, we created a Gantt chart to monitor our progress during the duration of this course when working on the main task. We spent around 3 to 9 hours per week working on our GPS tracker, which would vary depending on each week. We had team meetings lasting for approximately an hour each every week, and most of our time was spent on working on the written deliverables, developing the product, and test running it. Our team did have some setbacks due to the Neo 7M chip being broken, as mentioned earlier. After several tests, we had to order a new one, which caused a few unexpected delays in the project, such as getting the GeoBud to run with this new chip and printing the casing. We completed 6 tasks in total and 11 subtasks in order to create our tracker. And that concludes our presentation on the GeoBud. Thank you for watching.